Okay, well, thank you all for being here today. I'm really glad to present this project, which is called BlackIce, a containerized red teaming toolkit for AI security testing. It's something that we use internally at Databricks as part of our AI red team, and we're glad to be open sourcing it. This work was done in conjunction with my colleague Alex, who's here today, as well as our former manager Neil, who wasn't able to join us. So for the talk, I'll begin by just giving an outline of what I'll present. So starting with the motivation, really the goal here is to try to make a containerized toolkit similar to Kali Linux, in the sense that we want to bundle a bunch of penetration testing tools that can be used so we can automate processes and make ourselves more efficient and effective. In terms of the tools, we included 14 tools, and I'll present how we chose those tools and sort of outline the comprehensive coverage that they provide. Then I'll get into the specifics of the Docker image architecture and how we sort of unified all these tools within one system, and then how you can extend it for your own use cases. And at the end, I'll present a demo showing BlackIce in action on the Databricks platform, and I'll take questions if there are any at the end. So starting with the motivation. There are many great AI red teaming tools. Like, for example, you just saw Pirate. This is one that's included in the toolkit. And we can sort of classify them into three primary domains. The first being responsible AI testing. So this was sort of outlined previously, but this is like policy compliance, bias, and hallucinations. Then there's security testing for AI models and systems, which can include direct and indirect prompt injections, privacy leakage, and data leakage, or like pickle file scanning and things like that. And then we also have classical adversarial ML testing, because there's, of course, still sort of classical machine learning classifiers that need to be tested for adversarial robustness and model extraction. So, well, there are all these great tools. There are still some challenges. So one of them is that each tool has its own unique setup procedure and configuration, and having to do that for each one can be complex and time-consuming. Another aspect would be interoperability between tools. Some of these tools are more static scanners. Others, like Pirate, are sort of custom Python frameworks, and you may want to use multiple tools in conjunction together. And in terms of scalability, it would just be really helpful, in our opinion, to have like one Docker image that has all of these pre-configured, pre-installed. We can automate the testing that we want to do. And particularly for Databricks, where we use managed notebooks, this only uses a single Python interpreter per kernel. So given that there's dependency conflicts between these tools, if we want to include, to import like multiple tools in the same notebook, we need a way to be able to do that. So, and I guess the last point would be that there's a high barrier to entry. So there's many different tools, and it's not always clear which tool to use for which use case. So like I mentioned, for Kali Linux, this problem was solved by bundling many penetration testing tools into one ready-to-use Linux distribution. And this really allowed red teams to bypass setup hassles and focus on what really matters, which is AI security, or security testing in that case. And in our view, it would just be beneficial to have a similar toolkit for AI red teaming. So what we came up with is BlackIce, which, as I mentioned, it's a Docker image that bundles 14 tools together. As it's an image, it's portable, it works locally or via cloud platforms. We unified the command line interface for all tools, and we made the Docker build process very modular and extensible, so it's easy to add new tools, and we can even patch the source code of existing tools, which I'll describe if that's necessary for your use case. But first, I'll just discuss the tool selection and coverage that the toolkit provides. So in order to select the tools, we basically looked at different aspects. So we identified some critical threat domains. We reviewed system cards that document real-world red teaming processes. We analyzed outcome from competitions. We discussed with AI security practitioners. And what we came up with was these 14 tools, and we hope that it sort of represents many different tools across the spectrum. So we can see here that there's tools from industry-leading teams like NVIDIA, Meta, and Microsoft, from some AI security startups, academic researchers, and even one called PromptMap from an independent researcher, which we found to be useful. And in this table, you can basically see the organization, if there is one that supports it. the number of stars from the GitHub repo as of several weeks ago, and the source where we download the source code during the Docker build. Just as a sanity check, we wanted to basically map the capabilities of BlackIce to AI risk frameworks. So MITRE Atlas is one that's well known. We also have the Databricks AI security framework. So you can basically see here that within BlackIce, it's possible to test for direct and indirect prompt injections, privacy leakage, hallucinations, classical adversarial ML testing, supply chain and artifact safety scanning. And these are just some of the capabilities that comprehensively the tools provide. So now I'll get into the specifics of the Docker image architecture. Basically, for those of you that aren't familiar with Docker, the idea is that you can define a Docker file, which when it's built, you'll get this pre-configured environment with everything installed as you explained in the Docker file. So this is basically the build workflow, so how we laid it out. I'll go into each of these aspects in more detail in the following slides. And at the top of the Docker file, we basically have these tool lists that sort of organize the configuration during the installation. So this I'll explain as well. And then we have build artifacts that are brought in during the build. So starting with creating the different runtime environments for the different tools. We have this distinction between static and dynamic tools. So in our case, static tools would basically be CLI-based structured evaluations that require minimal coding. So you can just run a command and launch an assessment. These, in our view, they don't need to be interoperable. You can more or less use them in an isolated environment and they can work out of the box. So some examples would be PromptFoo and Garrick. And alternatively, like Pirate, we have dynamic tools that are Python frameworks that support custom workflows. And in this case, you would want them to all be installed in the same environment because they can work together. And we basically just manage conflicts in a global requirements file. So Pirate and rigging, like I said, are examples of dynamic tools. Just to provide a bit more clarity, here we can just see how some of these static tools are run. So really it's just a CLI command. You define your arguments. Maybe you'll make a REST JSON file for Garrick and they can launch out of the box, but it's pretty straightforward. This was taken from the Pirate documentation, but basically here we can just see, so you're going to define like the different aspects like the score, the attacker and things of that nature, and then you'll write your own Python code to basically launch the attack. So now that we understand the distinction between static and dynamic tools, I'll discuss how we retrieve the source code for the different tools and then apply patches before installation. So here we can see, like at the top of the Docker file, I know it's a bit difficult to read here, but we just have a couple tool lists. So one would be the Python tools. And in this case, basically all the tools that are written in Python are defined. If their version is specified, then the source code will be downloaded from PyPy. If it's not specified, then that would mean that it should be included in the Git tools. So here you would want to make sure to include like your Git URL, a reference for the commit hash or the tag, because we want it all to be reproducible and version controlled, and requirements file if it exists, or the PyProject file if not. So this is one functionality that we found to be very useful. So we basically support patching of the source code before installation. So this is just one specific tool called Cybersecurity Benchmarks. Natively, it supports connectors to like OpenAI, Anthropic, and other model providers, but it didn't support a connection directly to Databricks model serving endpoints. So what we did is we can just add a diff file that will modify the source code during the installation. We can add a new file path for the specific Databricks connector. And the nice part about this is then out of the box, we have this Docker image that will have this tool working as we want it connected to Databricks. Next, I'll discuss actually installing the tools to their environments. So this is just pseudocode. It's a bit more complicated than this, of course, but the idea is that you have dynamic tools that in general are installed to the system level Python environment, and then you'll have static tools that are installed to their own isolated runtime environments, and then we use the global requirements file to manage system level dependencies. But I should note that there are some tools that, according to our definition, would be dynamic tools. These are mostly used for like classical adversarial ML testing. They have a lot of legacy dependencies. So for that reason, they weren't able to be included in the system level Python environment, but they have their own Python virtual environments. They can be used, just maybe not invoked directly from like a managed notebook service where there's one Python interpreter. Additionally, a lot of these tools, if you look at their dependencies, so there's some heavy dependencies. For example, a lot of them require torch. I found this out of the box that if the torch is included as a dependency, it will automatically install the one with CUDA, which is quite heavy. So we wanted to make sure that the Docker image is as lightweight as possible. So in the end, with the 14 tools, it's about 4 gigabytes. So it's not excessively large, but if we included the CUDA dependencies for all of the torch installations, it would grow rapidly. So for this, we just have a simple torch constraints folder with these files where we basically just map to the requirements from the PyProject files and add the CPU tag. So we know that it'll pull in the CPU version, and this keeps everything lightweight. But if you'd like to change it, it's very simple. So you can just modify there, add CUDA for whichever version you want, and then that specific tool will have access to GPUs. So this is useful, and for any heavy dependencies in the future, there weren't any that we came across yet, but if they were to exist, this is like a simple framework for addressing that. And then lastly, we wanted to make it simple to unify all the tools across the CLI so they can all be invoked directly. So basically what we did is for all of the tools, if they already had a CLI implementation, then we basically just wrote a wrapper that at minimum would sort of point to the correct Python interpreter to make sure that the tool can run out of the box. Or you can use a CLI to like create a CLI for a tool that doesn't natively have one, or you can extend the CLI capabilities. Yeah, so basically we just use symlink. So we just make a symlink in a user local bin directory that points to the CLI scripts. One kind of interesting thing is that you can actually have a tool that's just a CLI script. So we have a simple tool that we included called Bias Forge, which is something we use internally to assess bias in LLMs. And from there, through the Docker build process, you can then like invoke that directly from the command line. So we find this to be useful. Now I'll go over the demo, but I first want to mention that really with this Docker container, the idea is that you can use it locally, but really you can automate your testing. So for example, at Databricks, what I'll show in this demo is that, let me first start the demo and then I'll talk through it. So here, for example, we want to create a compute. So we have the BlackIce image. So this is using something called Databricks container services. So the idea is that within the Databricks platform, you can pull in an image from Docker Hub. So now this is public. So this was using the BlackIce test image, but now this will just be BlackIce, and I have the link at the end. So then you can create this cluster. You can do this in Databricks. You can do this in any cloud platform, really, because it's a Docker image, so it's portable and can be used across the board. And now you would connect the notebook to that cluster. So here we already have it connected. But you can see that out of the box now, these tools just work, right? So normally, for example, you would need to install the tools, manage the dependencies, but even they couldn't all be used in the same notebook environment because this notebook has one Python interpreter per notebook kernel. But because the static tools are running in their own virtual environments and they're all accessible via the CLI, you can see that that's just directly runs out of the box. So here we basically write some Python functions which will run the various tools. And we can assign like the environment variables, like the base URL and the API key. And then we also have the command below that you would run for the specific tool. So this is for prompt map, but basically you can define these functions and then you can put it in a script and then you can make a job and then you can basically run all of your testing just out of the box for these tools. So here we just show you one defined for a single tool prompt map, but we have below the ones that we import for all of them. Yeah, and I should mention here too that the results, basically what we're showing in this demo is that they'll just be like a little data frame showing the output across all the tools. So here we have the success rate. So then we just import these functions like in a runner. And again, this is in a notebook, but you can imagine just like having this as a script and just running it all out of the box. So we import these tools. So here's where we actually define it. This is kind of where it's interesting. So across the different attack types, here we're looking at prompt injections and jailbreaks. There's different tools. Different tools have different attacks. Some could be more interesting than others for your use case. And it's sort of just putting them all together in one self-contained environment. So we can see here that for the different tools, we've selected different attacks, and then we can just pass in the arguments that we need in order to run those. So here we're looking at the prompt injections and then the jailbreaks. So we're using, I think, Garrick, CyberSec Eval, Fuzzy AI, and Prompt Map for this demo. Then we just define a function that for running these various tools. You have the Garrick runner and a runner for each of the tools that I mentioned. And then lastly, we have this function. So it's just going to sort of run through the tools and get an output. We sped this up because these tools typically take some time to run, but essentially all the tools will run here, and then it will output a data frame just showing the attack results. Yeah, so this part's sped up. It'll just take a bit of time. Mhm. And then in the end, we'll just output on the bottom just the results here in the table. So yeah, basically you can see that there's the different types of attacks for the different tools, and then you can look at the success rates. This is the end of the demo, and that's what I have to share with you today. So basically, this is an open source tool. We hope that you'll find it useful. We certainly find it useful. We use it during our red teaming operations. You can pull it directly from the Databricks Docker Hub, and I think there should be an updated last slide to this. Maybe I'll give that to the coordinators, but that should have the correct link to the GitHub repo where you can find all of the build directory. So the nice part about this is if you want to add new tools, you can just take the Docker file, modify it yourself. It's very clear in the README how this all works, and you can build these containers and use them for your purposes. So thank you very much for your time, and I'm happy to answer any questions if there are any.
This is a great idea. I think it democratizes access to a lot of these tools, sort of lowering the barrier to entry now to people that are familiar with Docker and Python. I was wondering, I'm sure everyone in this room is probably pretty skilled with these tools, but to make it even easier to use, have you guys considered making some sort of GUI so that people don't even need to be familiar with Python and such?
Yeah, I think that would be a good idea. It could definitely be useful, particularly for the static tools that run out of the box. Like, if really the main thing you need for those static tools is just setting some environment variables. So you need like the model endpoint that you're going to query. Maybe you need the API key and things like that. But I agree with you that having a simple GUI where you could just put in those environment variables and then run the evaluations, that would definitely even further lower the barrier to entry for people.
So maybe a dumb question, but it looked like you didn't have Robust Bench as one of your tools. And I was wondering if you had looked at it and if you decided not to use it.
I don't think we did look at Robust Bench, but but we can definitely take a look at it and include it in a later version of the release. But the good thing too is like, say for example, for your use case, if you wanted to use robust bench, all that you would have to do is add a single add robust bench to the Docker file and then build the image, and then you have it exactly as you want. So this, I would say, it's more of a template for people to use. Like obviously one can pull like the existing image from Docker Hub, but the idea is that anyone can add any tools that they find interesting, any tools that they want, sort of patch the tools as they see fit and use it for their purposes.
Robust bench is a really good one for adversarial examples. So just so you know.
Yeah, thank you.
We're out of questions? Okay. Oh, we have one more. Sorry.
Thank you. I appreciated that. I am curious about how you do attack success rate calculation across all the different tools. I assume that each different tool has kind of a different way of doing ASR. And then also, is there a way to see what the actual response is from the model after the fact, or is it just mostly at the table and you kind of see this played out?
Yeah, so full disclosure, my colleague Alex made the demo, so I'm not exactly certain how the attack rate in this specific demo would be demonstrated. But really, I guess this was sort of like a simple example. Like this wouldn't necessarily be exactly what we would do. Like maybe internally, what we would have is anytime like a new model endpoint is added to like Databricks model serving endpoints, what we could have is we'd have an automatic job that sort of scans like what models are added. Then if it's added, it'll just like trigger this to run, and then we could generate like an automated email report that then send out to stakeholders like showing these are the attack success rates. It is a challenge though. Like here, where we showed the specific attack success rates for the type, it's still not clear because it depends like who you're talking to. Like if I showed the success rates individually for each attack, maybe to you and I, that would have meaning. But to someone who's just trying to understand like how vulnerable is it to prompt injection, showing like the results from 15 different types of prompt injection attacks, maybe they're not clear like exactly what each one means. So I think that's still an open challenge. And I guess it depends on what we're trying to explain and to who we're trying to explain it to. Did that answer your question?
The second part of that was for, like if there's something that has a successful attack, sometimes we want to pull that specific response quote, right, and put it into our stakeholder report or kind of highlight those specific things. So I'm wondering if there's a way to get those specific responses also from each tool.
Yeah. So basically, really, this is just like you can think of it like an operating system for running these tools. So everything that you do in Pirate would be done here. Like if, for example, I want to use in that notebook, if I want to run Pirate, I can just load in like a memory instance and use that just as you guys would use. Or for example, for Garrick, I can just save the output to an output file, just put it in as an argument. So yeah, it's basically just what we use it for is primarily for running all these tools in one single environment. Because the problem that we were primarily trying to solve, I guess, was number one, how can we use all these tools specifically in like a managed notebook service where there's just one Python interpreter, given that they all have dependency conflicts? And second, how can we just have like a consolidated Docker image that would allow us to sort of automate these processes across like multiple tools?
One more round of applause for our speaker, please.